Now we need to calculate, guys, we need to calculate the work done by gravity. So, in order to calculate the work done by gravity to move an object up or down, to move that object up or to move it down, all what we have to do to calculate the work done by gravity is simply to do the following. It's the force dot the displacement. So, if I move that up to this distance d, what is the force of gravity on that object? What is the force of gravity on that object? It's mg. It's mg. This is the magnitude of the force of gravity on that object. In what direction is the force? Downward, right? Downward. This is the direction of the force. Now, what is the displacement? It's d. I moved it up a distance d. What is the direction of the displacement? Up. Now, if we try to find F dot d, force dot displacement, work done by gravity, in that case it's force dot the displacement. The force, you said that's going to be mg. The displacement is just d times cosine the angle between the two vectors. And the angle between them is 180 in that case that I just gave you. Then in that case, the work done is going to be minus mg times d. D is the height. Okay, now if I want to move the same object from that position, Nagy, to the chair, back. So from here to here, which is the distance d, and we need to calculate the work done by gravity, to move it from that point back to the chair. So what to do? Once more, again, the work done equal to the force dot displacement. Nagy, what is the force in that case? mg times that distance, the magnitude of the force times the distance, d, times cosine the angle between the force and the displacement. Now, if you move it down, what is the direction of the force? Down. What is the direction of the displacement? The angle between them, between those two vectors is 0, that's cosine 0, then you get mg times d. So now we know how to calculate the force done by gravity to move an object from position to another. Now, assume that I'm going to move that same object m from that position to that position, a distance delta y or distance d, doesn't matter, that the symbol will get to that distance. But along this funny path, to here, then to there, to there. And I will calculate to you guys what will be the work done in that case. So I'm going to say the work done in that case is going to be the work to move it from here to here, which is going to be F gravitational force dot delta R1 Nagy plus the mg dot delta R2 plus mg dot delta R3 plus mg dot delta R4, and if I keep doing this, and if you keep doing this and add all those forces together, so it's going to be F dot delta R1 plus delta R2 plus delta R3 plus delta R4. That's if you take the force as a common factor. Let me finish. Okay? And if you keep in adding up delta R1 plus delta R2 plus delta R3, you will get this green vector, that's delta R, from the starting point to the end point. And if you do F dot delta R, you get F times delta R times cosine the angle between the force and delta R, cosine that angle. And you can, if you look at that triangle there, this triangle there, if you call that angle theta between the force and the vector delta R, if you call it theta, delta R cosine that angle theta, it's that height, delta y. So you get F times delta y. The same we get if you move it straight from that height to a height below, to a point below it by a distance delta y. And in that case, we can conclude that the work done by gravity does not depend on the path. It does not depend if you move that object from here to that point, or you move it that way back to the point. The work done in the two cases is the same. The work done does not depend on the path. Yes, Taha.
When we add delta R1, delta R2 with the force, does the force change?
No. The force, all the time, the force by gravity. The gravitational force. And the gravitational force, that's always mg. I choose the I coordinate to be j. This is my positive y. So for each movement, this is my coordinate. This is j, and that's x, for example. So I did not change the coordinate. Did I answer you? Okay. So the work done is going to be minus mg times delta y. It depends only on the delta y, and it does not depend on how did we go from the starting point to that point. It does not depend on the path. It depends only on the height. Okay, guys. How about multiple forces? So far, we have calculated how can we find the work done by an object if you push it or if you move it, but with only one force, single force. But if you have multiple forces, what are we supposed to do to find the work done in that case? Simply, you find the work done by force number 1, the work done by the force number 2, the work done by force number 3, then we add them. And torque is saying it's exactly as if you take delta R as a common factor between them, you end up having F1 plus F2 plus F3 plus F4. You add them as vectors and you get the net force. So if you add them like Milna said, that's what you get. F1 dot delta R plus F2 dot delta R. If you take F1, if you take delta R as a common factor, Nagy, then you get F1 plus F2 dot delta R, and F1 and F2, those are addition of two vectors. This is, we call it the net force. So it's exactly as if you do the total force or the net force dot delta R. So if we have multiple forces, there is no problem. We calculate the work from each force and we add them, or we find the net force and find the work done by the net force on that object. Now, who's on diet? Who's on diet? Ali, are you on diet? Yes. So Ali is on diet. Now, I'm going to ask you something. Let's assume that you're going to say that you're going to exercise every day, and you'll go every day. You're going to go up the stairs and down the stairs every time you leave your house or you go back to your house. And you decided that to lose more energy. You decided to run up the stairs. Then someone came to you and said, no, actually, if you run up the stairs or you walk up the stairs, you're going to exert exactly the same energy. You're going to exert exactly the same energy. Is he correct?
Yes.
Okay. Before we go into debate, so let's just gather all the answers first. So I decided to run up the stairs, and Vanessa told him, no, if you run up the stairs or you walk up the stairs, you're going to put exactly the same energy. So some people said yes, some people said no.
dependent on the acceleration.
The work done is down. Does the work done depend on the acceleration?
Yes, it was with the mass and the acceleration.
Oh, okay. I'll say that a different way. I'll be more specific. He decided to run up the stairs by, but it's the work is by velocity equal to 10 meter per second or velocity equal to 50 meter per second. Constant velocity for now. I did not talk about power. And we did not study anything about power yet.
But you're going against gravity.
Yeah, but he, in the two cases, he's going to run against gravity. He's going to go up the stairs either by 10 meter per second or by 50 meter per second. So he's going to work. He's doing work against gravity, and the work he's going to do, it's exactly the work done by gravity on him. This is conservation of energy. So the work done by gravity on Ali is going to be mg times d, and it will not depend on if he runs fast or runs slow. He's going to lose the same energy. It's m, it's the force dot displacement, and the force in that case, that's the force done by gravity, mg, not ma.
Doctor,
Yes.
isn't kinetic energy equal half mv squared?
Yeah.
So he will have more kinetic energy than.
You will lose more kinetic energy.
Yes.
But you're actually okay. I'm gonna raise that object from that location, from that position, Maggie, up with a constant speed, 1 meter per second. So I'm gonna start from 0, then I will take 1 meter per second. I will have a velocity of 1 meter per second. I will raise it up to 1 meter. So obviously, I have done some work on this. To raise it up 1 meter, I have done some work to raise it up 1 meter. Where did the force go? Sorry, where did the work go? Another form of energy. Before we go to potential energy. While it's moving, the force has gone into moving that object, so the force has gone into kinetic energy. As long as this is moving, the force has gone from work done, the work has gone from work that I do on the object into kinetic energy. That's why we say change in the work done will equal to the change in the kinetic energy. The work has gone into kinetic energy. Okay. Now we're going to jump into chapter 8. Now we go up. So I start to move that object. I will do work on it. And the work will go into kinetic energy for the object. Then I will stop. Where did the work go? It's stored in here as a potential energy. Now it's stored in this object as a potential energy. And any object, anything in life would love to stay at the lowest possible energy. Anything in life would love to stay at the lowest potential, at the lowest possible energy. That's why if I leave that object from some height that has some potential energy in here and I leave it, it goes to the lowest potential energy. So what happened now? Again, I move that up, so I will do work on it. The work has been transformed into kinetic energy. Actually, to be more accurate, it's kinetic and potential. As long as I move it up, it's kinetic and potential. Once I stop in here, all that work has been transformed into potential energy. Once I leave it, when I let go of that object, and when it falls down, that potential energy is being transformed into kinetic energy. Kinetic energy increases and the potential energy decreases until the point it reaches the ground. Now the potential energy is 0 and the kinetic energy just before it hits, the kinetic energy just before it hits the ground is maximum. Then someone will ask, and where did the kinetic energy go? Oh, thank you, Taha. Where did the kinetic energy go? Once it hits the ground, yeah, it has transformed into sound energy, and sometimes if you that drops on some sand, it will deform the shape of the sand, and the energy will go into the formation of the shape of the objects. Sometimes it gets broken. Wait. Okay? Okay, guys? Now, I'll take questions. Amira at first, then Tork, then Minna, then anyone else.
Here, how come the time is no, the velocity is constant, so there's no force, there's no
No. No. Yes and no. Yes and no. Yes and no. Yes and no. Focus on what I'm saying. I'm saying what is the work done by the gravity. I'm not saying what is the work done on that object. Because the work done on that object is the work by my hand and the work by gravity. I'm asking about the work done only by gravity.
Here it's same work by gravity, not same work by me, because
Yeah, and the work you do, it's equal exactly to the work done by gravity. But of course, you do work on this, and gravity do a negative work in this. You raise it up. What is the direction of the force of gravity? Down. What is the direction of the displacement? Up. This will give you a negative sign. So you're doing work equal to mg times h, but it's in a negative sign. What is the work done by my hand? The force of my hand, it's up. So it's F. And the displacement is also up. So it's F times h. That force that I'm doing by my hand, it's exactly, if I move it with a constant velocity, it's exactly equal to the force by gravity. If you move it up by your hand, by a force, and if that motion is by a constant velocity, that means that there is no acceleration. That means that the total forces on that object is zero. The net force on the object is zero. What are the forces on the object? mg down and your hand up. That means that the force you provide by your hand equal to mg.
But I have to do an acceleration, so it will be...
No, you don't have to do an acceleration. I can move that with a constant velocity. How come?
Because that's... no, I mean, when I do like this, then I do like this,
Mhm.
the work done by the gravity is zero,
Yeah.
but the work done
By my hand is also zero.
No, I will do it.
No. When you do this, the force you do is you push that object up. When you do this, the object is pushing your hand down.
But how come I get tired when I always do this?
No, you get tired when you're raising it up. But if you do this, you're not gonna get tired.
Zero.
No, it's doing work on you. The object does work on you. When you do this, who's gonna push what? Who's gonna push the other one?
I know, but if we kept doing this, the total work of the gravity is zero, but total work of me is 1, 2, 3.
Yeah, it's 1, 2, 3, because you're not counting the other part, the work done by the object on you.
How we do work is not the same thing.
Yes, it's exactly as if you raise this object up, then you bring another object and raise it up, and you bring the other object, third object and raise it up, and you bring the fifth object and raise it up. So you keep doing work. You keep doing work, and this is not the whole cycle. The whole cycle is if you raise that up and you let go of it to do work on you, then the total work done now is zero. And by gravity is zero. Excuse me? You get tired because you keep doing work. You keep raising it up.
Then we bring it back down, now it's neutral.
Oh, because you resist the pushing of that object. So you have to do work as well. to resist. But if you do not resist, you let go, you're not gonna do any work.
Yeah, so it has to.
So actually, and you don't have to, and no one has told you to keep your hand that way. If you let go, it will drop by itself. Right? But if you decide to keep your hand that way, that means that you have to provide resistance to the motion of that object. But if you let go, it will fall freely due to gravity. So you keep tired because you push it up against gravity. That's one. Then you get tired again because you keep resisting it to fall down.
So I do your work, but
Oh, yeah.
yeah, so it's 2, 1, 2, 3, 4.
Yes, yes.
It isn't 0. It isn't like, it isn't the output.
Total work will zero. The work you do.
Yeah, true. The total work done by gravity is 0. But what you do is you provide force to push it up, and that's work. You do work to push it up, and you do work also to resist it from falling
So it isn't 0.
by you.
Yeah.
But the gravity it's 0.
Yeah, so here it means the same work by gravity, not me, because when I go quick,
No.
I do more work
No,
than when I
no. When you go quick, the work you do is the work against gravity.
Okay.
The work you do is exactly the work against gravity. And the work, if you go up very quick or you go very slow, the work done against gravity is the same. You have to provide with the same force. It's mgh.
So how come I get
Y-
I go
Because this is something biological. You're putting your heart to beat faster, and that's why you get tired. You have to, your heart as a machine, as a pump, it has to provide blood enough for your muscles. And your muscles work harder, but actually what you do is, you do this, Hassan said something. You do the same work over 15 minutes to go up, or over 1 minute to go up. And this is power. Work done per unit time, this is power. So you accept the power is going to be different, the power is going to be different, but the work done is going to be the same. Okay? So the work done is going to be force dot displacement. Now, we have 3 cases to have work done equal to 0. That's if the force is 0, if there is no force, the work done is going to be 0. If the displacement is 0, so if I push in that object, like that, the work done is 0. But if you do this, there will be some work done. Work done is 0 because even though, yes, thank you. Even though I'm pushing on it, I'm putting some forces on it, but the displacement is 0. So this is the second case that we get 0 work done. Or third one, if the angle between the force and displacement is 90. Now, what is the work done by the tension force on that object? So this is an object that we hang it from somewhere in here, and it keeps oscillating. This is a simple pendulum experiment that you have in the lab. So if you have this as a simple pendulum, so what is the work done by the tension on that object? Okay, so, we said 3 cases that we get work done equal to 0. Either the force equal to 0, is the tension equal to 0? No. Is the displacement equal to 0? No. Is the displacement and the force perpendicular to, are the displacement and the force perpendicular to each other? Yes. Displacement, this is the direction of the displacement, and the object keeps displaced. So to move it from up to here, what is the displacement? So at any point, the displacement is, the work done is going to equal to 0 because that angle, the displacement and the tension are perpendicular to each other. This is the work done by the tension. By the tension. Only the tension.
The work done by the object, which is
There is no work done by the object. The work done is always by a force. The work done by gravity is going to be mgh. Change in the height, yes. It's mg times the change in the height. Excuse me? Yeah. So now, what is the work done by the disk? By the normal force? If this is the displacement, normal force is always perpendicular to the surface. That means that the work done by the normal force in that case is going to be 0 as well. Excuse me? No. Why not? Oh, yeah. Yeah, but you have to understand that it's 0 because the normal force is always perpendicular to the direction of the motion. Okay, now, Farida, we have 3 objects. Those are Shaib, 3 objects. 1, 2, 3. We're gonna move them from that level to that level through 3 different paths. That way, and that way. And I'm asking you guys to compare the velocity for the first case, Vf, to the velocity of the second case, Vi, in here, to the velocity of the third case, Vp, in here. But I'm talking about velocity. I'm talking about velocity. So what you're saying is the change in the work done for the 3 of them is going to be mainly due to gravity, and the work done in the 3 cases is going to be mg times h. Correct. That's the work done. I'm talking about the velocity. Samira? Wait. This is not a way to discuss things. Amira?
the change in the kinetic energy equals the work done.
Yeah.
So when the work done increases or decreases, it corresponds to the
Change in the kinetic energy, of course, yes.
so the velocity is the same.
Is the same. Since the change in the work done for the 3 cases is the same, the change in the kinetic energy for the 3 cases is going to be the same. If all of them start with 0 velocity, they have to end up by the same velocity. I'll say it a different way. If they all start with the same velocity, they have to end up by the same velocity at the same level. Okay? Good question. Of course, you're right. Not at the same time because they will travel different distances as you see. Okay, but initial velocity and final velocity, they have if they have the same initial velocity, they will end up with the same final velocity. But the time to change that velocity is going to be different, and if you think about it, the acceleration is going to be different, and that's what will make the time different. The acceleration here, that's mg. The acceleration here, the acceleration here is just g, acceleration due to gravity, because that's free fall. The acceleration here is going to be mg sine that angle. Sine that angle. Acceleration here, that's it's a little bit of calculation. That's not that easy. Sharif. No, they will not have the same speed. Oh, same speed at the end? Oh, magnitude of the velocity. Yeah. Magnitude, yeah. change in the kinetic energy. Yes.
Will that constant will be equal distance to the delta in the
V equal to distance times time. This is correct. Why not? Yeah, only if acceleration equals to right? Good. Right? Right, guys? Vanessa, right? Are you sure? Should I explain that a little bit more? Good. Yeah. Regardless. You're right. It's velocity equals distance over time. Only if the acceleration is zero. Not constant. Someone said constant. No. If it's only equal to zero, if the acceleration is equal to zero. If the acceleration is constant, velocity, yeah, x will equal to x0 plus v0t plus 1/2 at squared. This is equation that gives you a displacement if the acceleration is constant. But if it's zero, then this term is zero, and if you have x0 equal to 0, then x equal to v0t, or v equal to x over t, the same thing you were saying. What? Excuse me? A? No. I don't think we have ever said that acceleration equal v over t. Thank you. If we talk about instantaneous acceleration, it's dv by dt. If we're talking about average acceleration, that's delta v over delta t. Okay, now we have studied how to calculate the work done by one force, the work done by multiple forces, but in all cases we have assumed that the force is constant. It does not depend on the distance. The force is constant. But now if you have a spring and they have a mass attached to it, and if you pull it that way, what is the work done by the spring on that object? Again, if you have a spring, and there is an object attached to it, so there is a spring between my two hands now. This is the object. Okay? So if you pull that object, then what will be the force done by the spring? The force done, we know that the force done equal to negative kx. That's correct. Or delta x. Delta x is displacement from the initial location to the final location. Now if you displace it a little bit, a small distance, the force is going to be small. If you displace it a little bit more, the force will increase. If you displace more, the force increases. So the force depends on the distance. So we cannot say that the force, the work done, equals the force dot delta x in that case. This cannot be, because the force depends on the displacement. But we can do this. I'm going to say, I'm going to move it very tiny distances, very small distances. Along that small distance, I will assume that the force is constant. If that delta x is very, very small, then the force is going to be almost constant. Then I will calculate the force in that case, which is F. Then I'll call it F1. I will multiply by delta x. This is the work done. If you move to move that very, very tiny distance or displacement, then you move it a little bit. The same delta x, the force will change. I will call it F2. Multiplied by the same delta x, you get W2, work number 2. Keep on doing this. Then add up all those work done, and this is the total work. So someone will say, how small should I divide that delta k? as small as possible, because if you get delta x, if you get delta x almost to be 0, the force is going to be constant along that period of delta x. Then we can apply that work done equal force to delta x. And this is exactly the meaning of integration. This is exactly the meaning of the integration. So what you do is, what you have to do is to draw the relation between the force and x and find the area under that graph. This is the work done by that force. So if we draw a force as a function of the x, you increase the force, you increase the displacement. Forget the negative sign for now because it means direction only. The magnitude of the force as a function of x, that's what you get. If you want to move it from x equal to 0 to x equal to 10, if you find that area, then this is the work done. This is the work done by the spring. Or, this is graphically, or do the following. The work done in that case is the integration to move it from 0 to 10 for f dot dx. So it's the work done to move from 0, Mahmoud, to 10 for f, which is kx dx. K is constant, it goes out of the integration. What is the integration of x dx? Then you get k times x squared over 2 from 0 to 10. If you put the limits of the integration, then you can calculate the work done. But if we need to move it from 0 to any distance, I will call it x, then the work done is going to be half kx squared. So simply, if you have non-constant force or variable force, all what you have to do is either to grab the relation between the force and the displacement and find the area under the curve. That's what exactly. Nada? Nada? What's it? Oh, okay, Minna. Minna. So you draw that relation. Then you find the area under the curve, and that's going to be the work done. And sometimes the area under the curve is not going to be easy like that example in here. So you draw this curve, and that's funny shape, and actually it seems even harder to find the area under the curve. Or what you have to do is the following: divide it into small parts and find the area of each part of them and add them together. And this is exactly the integration. So simply we can do the following. It's the integration to move the object from x1 to x2 for f dx.
So we could use this equation.
This is for the method for the spring.
Yeah.
Yes, only for spring. But sometimes I can tell you this. There is an object that's doing work with a force equal to 2x squared plus 1 plus x plus 1. This is the force. Find the force done to move the object from x equal to 1 to x equal to 10 meters. So simply, the work done in that case is equal to the integration from 1 to 10 meters for the force 2x squared plus x plus 1 dx. So that integration, I will remind you by that integration, guys, it's 2 times x to the power. We add 1 to the power and we divide by the new power plus x squared over 2 plus x. From 1 to 10, and if you put the limits of the integration, you will be able to find the work done to move the object from x equal to 1 to x equal to 10 for that function, for that force. Okay? This is only for spring. For spring, this is the potential energy for spring. Thank you guys. I will see you on Saturday. The class will